Thank you very much. Thank you for coming. Hi everyone. I will be talking about jointly learning word representations and composition functions using predicate argument structures. Recently, as you know, learning word vector representations using neural networks with large unlabeled corpora has attracted much attention. It is said that such word vectors can capture syntactic and semantic similarity between words. Such work includes the well-known toolkit word2vec, which can run vector representations for single tokens. And more recent work has started incorporating compositional processes into neural network language models to run word representations and their composed vector representations. In this presentation, we focus on some points for these kinds of work. These four points are listed in this table. First, word2vec-like models can run vector representations for single tokens, but cannot capture composition of words. And convolutional neural network language models can run composition of words, but such models often require high-quality word vectors pre-trained by other models like word2vec, and do not capture recursive structures of multiple syntactic relationships. Compared to this work, our model satisfies all of the 4 points as presented in this slide, in this presentation. So then a question arises. How can we jointly train word representations and their composition functions using syntactic structures from unlabeled corpora? To answer this question, we introduce a joint learning model to run word representations and composition functions using syntactic structures from unlabeled corpora without using any pre-trained word vectors from other model. Here is an image of our goal, describing our goal. Some words are embedded into a vector space, and what we'd like to achieve is to embed these representations in red into the same vector space, like this. So hopefully these vector representations capture syntactic and semantic similarity between words and composed vector representations. By using our proposed model, we achieved state-of-the-art scores for phrase similarity tasks with transitive verbs, as shown in this presentation later. This is the overview of this presentation. First, let me introduce our model to run word representations using predicate-argument structures. As widely known, dependency structures are relationships between heads and their modifiers. Here is an example of dependency parsing. Compared to this, predicate-argument structures, which are often abbreviated to pass, are relationships between predicates and their arbitrary number of arguments. Each predicate in a sentence has a specific category and there are arbitrary number of arguments. Let me show you some examples using this short sentence. Heavy is a predicate with one argument, rain, and the category here is adjective with one argument. And next, cause is a verb with 2 arguments. And next, car is a noun with 1 argument. Builds on these kinds of paths. Given a path, we would like our model to discriminate between a word in the path and a word drawn from a noise distribution. In this example, first, we select a word as the target word. In this case, cause is selected as the target word to be predicted. Then we assume a noise distribution to draw some noise words from the distribution. And in this presentation, let me select eat as the target, as the noise word to run our model. And the other words, rain and accident, and their syntactic information are treated as context information to determine which word, cause or it, is appropriate to the given context. Now let me describe our model in detail using this example. First, context word vectors are embedded into a vector space. And then we provide them with syntactic information of them. In this case, the information is that rain is the first argument, and the accident is the second argument of a bar. And then we compute a feature vector, P of cause, to estimate how well the target word cause fits the given context. P of cause is computed like this. Each input word vector is weighted by a weight vector, which is dependent on the specific categories of predicate argument structures, like this. Then using this context information, we compute the dot product S between the feature vector P of cause and a weight vector for cause. The higher the value of S is, the better the target word cause fits the given context. Similarly, we also compute the dot product S prime between the feature vector and a weight vector for it. We train our model by making the value of S prime relatively smaller than the value of S. To achieve this, we define the cost function like this, and by minimizing the cost function, our model can be trained via backpropagation algorithm. Now let me explain what we expect from the model. Via backpropagation algorithm, word representations can be efficiently trained based on the information of past categories and selectional preferences. In this example, the information of cause and it are propagated and summed up, and then finally they are fed into the input layer. Input layer is the word vectors. What we can see in this example is that rain can be a subject of cause, but not it, and rain can cause accident, but rain cannot eat accident. By such information, word vectors are trained around efficiently. These are the additional two examples. In the left case, eat and at are the context information, and the target word is restaurant here. And in the right case, the context word is rain, and the target word is heavy. So far, we have assumed that the context information in our model is words in a path, but the number of words in a path is often limited, like this. So we provide additional context information using nouns and verbs in the same sentence. For example, if the two words road and injure appear in the same sentence, we feed the vectors of them into our model, like this. By doing so, our model can capture richer context information during training. Okay, so as described above, currently our model can run word representations using predicate argument structures. But according to our goal, we would like to obtain vector representations composed by multiple words and their syntactic relationships. Here is an image of examples. The two words storm and downpour are embedded into the vector space. And we have a path, right, like heavy rain. Then what we would like to achieve is to embed the representation of heavy rain into the vector space. And hopefully these vector representations are close to each other in the vector space. But what can our model achieve this? A very simple approach is to treat a path as a single token. For example, in this case, if the two arguments, rain and accident, are connected to other words by other paths, like this, then we treat the relationships of two words, heavy and rain and car and accident, as single tokens. In other words, we independently parameterize the vector representations of heavy rain and car accident, like this. So currently, there is only the change at the input layer. So there is no model change at all. Now, to verify our intuition behind the model, we trained the proposed model and inspected the round vector representations by showing similar tokens for each path representation in terms of cosine similarity, like this. The table clearly shows that the round vector representations can capture some sort of syntactic and semantic similarity between word and composed vector representations. Here is another table showing that examples for verb-related phrases. This table also shows that some sort of semantic similarities can be captured, and these results suggest that our model works well, but at the same time, some issues arise, and the issues motivated us to incorporate composition functions into our model. Next, let me introduce our joint learning model in this section. So first of all, why are composition functions needed? As described above, if we parameterize the path representations independently, our model has to have a very large number of model parameters to be learned. And of course, this leads to the issue of data sparseness. And another possible issue is that the pre-parameterized path representations ignore the very important information of individual words. To tackle these issues, we incorporate composition functions into our model. Instead of parameterizing path representations independently, we compose the vector representations using the word vectors in them. First, category-specific composition functions take the input word vectors and then compose the vector representations of heavy rain and car accident using the word vectors and some parameters, which is some parameters. And then the two composed vector representations are fed into our model, and still there is no model change at all in this blue part. And we would like to emphasize that any kinds of composition functions can be used in our model to train entire model. Okay, so in this work, we used very simple element-wise composition functions. Let me show the composition functions using the simple example of heavy rain. The first two functions are simple element-wise addition functions. And the last two ones are simple element-wise weighted addition functions. And the new weight parameters M are dependent on the categories of predicate-argument structures and trained during the model training. Okay, so again, we inspected the round composed vector representations by showing similar composed vector representations for each these representations in terms of cosine similarity. This table shows that our composed vector representations can capture syntactic and some sort of semantic similarity between composed vectors of verb-object phrases. And next, here is another table. And this table also shows that some sort of semantic similarity can be captured by a model for the phrases of subject, verb, object. And one thing we can see in this table is that head words are often strongly emphasized by our composition functions. To verify this, we listed L2 norms of the round weight vectors in our composition functions. This table clearly shows that for each predicate argument category, head words are strongly emphasized by the round weight vectors in our composition functions. Okay, so now that our model has been fully described, let me move on to the next section for empirical evaluation. Here are the overall experimental settings. We used the BNC corpus for our training corpus and extracted these 4 kinds of predicate argument structures for our model training. We used 50 and 1000 dimensional vectors in our experiments. The model parameters were optimized by mini-batch online learning using AdaGrad. For evaluation, we used 4 tasks of measuring semantic similarity between short phrases. 3 tasks for 2-word phrases, adjective noun and noun noun and verb object phrases. And 1 task for subject verb object phrases. Evaluation is done by measuring Spearman's rank correlation between human annotations and system output. More specifically, human annotators have given semantic similarity scores for all of the phrase pairs for each data set. And now what we should do is to output semantic similarity scores for all of the phrase pairs. And then for each data set, we can calculate Spearman's rank correlation for evaluation. These are the examples from the data set we used in our experiment. Okay, so let me move on to the main result, experimental results. This graph shows the scores for all of the 4 tasks we used in our experiment. The label human denotes inter-annotator agreement between human annotators for each data set. And we also provide a baseline using the toolkit word-to-vec. By training word-to-vec, we computed phrase vector representations by element-wise addition of word vectors. As shown in this graph, the word-to-vec baseline achieves quite high scores, especially for noun phrases. As shown here. And these are the scores of our models for different kinds of composition functions. And this graph clearly shows that our model can achieve high scores for verb-related phrases, like verb object and subject verb object phrases. And as expected, 1,000 dimensional word vectors consistently outperform 50 dimensional word vectors, 50 dimensional vectors like this, 50 and 1,000. Okay, so we then compared our scores with those of previous state-of-the-art work listed in this slide. First, this graph shows the scores for the 2-word phrase tasks. As shown in this graph, using 50-dimensional vectors, we achieved scores comparable to state-of-the-art scores. And using 1,000-dimensional vectors, we achieved new state-of-the-art score for the verb object phrase similarity task, as shown in this right graph. So let me move on to the result for the SBO task. Please note that state-of-the-art models often use very large corpora, like UK WEC corpus. But our model achieved the state-of-the-art score, as shown in the red graph, using a much smaller corpus, the BNC corpus. Finally, we inspected the effects of the bug-overs context used in our model. As shown in this graph, our bug-overs contexts are helpful in learning verb phrase representations. And in future work, we will investigate other kinds of bug-overs context, like window-based approaches. Okay, so now let me summarize this presentation. We have introduced a joint learning model to learn word representations and composition functions using predicate-argument structures, and achieved state-of-the-art scores for verb phrase similarity tasks. As future work, we are planning to incorporate more sophisticated composition functions rather than simple element-wise operations to improve verb phrase representations. Because, as shown in the result, there is a room for improvement for verb phrase similarity tasks. And we are planning to run full phrase representations rather than only 2 or 3 short word phrases. That's all. Thank you very much.
Hello. Yeah, thank you for the talk. I got some question about this subject verb object composition.
Yeah.
Can you go back to the slide? With your results.
This one?
Yes.
Okay.
Subject verb. So you got. What is the column? What is your result? Is it?
Each group shows the results for each data set, each different data set.
Okay.
Adjective noun and verb object and subject verb object.
Yeah, but I'm interested in the last one, subject verb object.
Yeah, okay.
So you get about 30, right? Little bit more, like 35.
Yeah.
Okay. So in our experiment, we also used BNC. And did you use all of it or some part?
All of the BNC codes.
Okay. Because if we just take verbs, our result is 60, little bit less. And I'm curious why your number is so smaller.
Compared to the human agreement?
Yes. And what we got? Actually, did you try, forget our results, but did you try just comparing to verb-only baseline, so just looking to the verb without doing composition?
Sorry, we have not tried yet, so I will do the experiment after the conference. Thank you very much.
That would be really helpful, because you will see how your composition is performing.
I see. Thank you.
Thank you, but thank you very much. I really like the paper and presentation.
Thank you very much.